We regularly use the phrase as simple as 1, 2, 3 to indicate that something is really trivial. However, that much of mathematics is actually built out of these natural numbers should indicate that there is something quite deep that you can learn from them. Now, if, like me, you are a regular visitor to the cyber world, you must have seen a rather strange result involving these whole numbers. That is this rather famous or notorious sum. The sum of 1, 2, 3, 4, in fact, all natural numbers. Now, if you have not seen this result before, I am pretty sure that you would say that such a sum simply cannot be done. Or you might say that this sum is simply infinite. Now, even those of you who know the result would find this rather difficult to believe. Apparently, this sum is minus 1 over 12. Not only that, this very strange and unbelievable result is apparently due to the great genius Srinivasa Ramanujan. Now, despite the name of Ramanujan being attached to this does seem to be an absurd result. After all, how can the sum of a bunch of positive numbers end up being negative? And you are adding a lot of whole numbers. How can the result be a fraction? Many of you who have seen this result before may have simply ignored it, assuming that this is one of the many crackpot results that is floating around in social media. And I would not blame you for thinking that. There is indeed a lot of garbage in social media, especially garbage which is peddled using big names. However, it so happens that this result is not completely untrue. Now obviously, minus 1 by 12 is not and cannot be the sum of a bunch of natural numbers. However, there is a specific sense in which this particular formula happens to be correct. We will try to explain what exactly is that sense and how does the result of minus 1 by 12 actually come about? Is this at all useful? And also, exactly what, if anything, does Ramanujan have to do with this? But this is a rather long story and it will take a reasonable amount of background information to actually understand what is going on here. So we will take this slowly and talk about this over several lectures. We will begin with something which is apparently very simple. The idea about what a summation really is in this context. Of course, we know how to add numbers. 1 plus 2 makes 3, 3 added to that makes 6, 4 more makes 10, and so on. But these are all finite sums. Now, most of you are also familiar with infinite sums as well, sums which are much more sensible than the one we are really discussing here. A sum like 1 plus half plus 1 by 2 squared plus 1 by 2 cubed plus 1 by 2 to the 4 and so on, all the way up to an infinite number of terms adds up to, and most of you know this result, 2. Now, in order to understand exactly what is going on here, let us begin by drawing a rectangle which is 2 units wide and 1 unit high. The area of that rectangle is of course 2 square units. We next draw a square of side 1 inside our rectangle. This is the red square that I have drawn. Its area of course is only 1 square unit, so there's quite a lot of space, exactly 1 square unit of space left empty at this stage. Let us now draw in that empty region a rectangle whose width is 1 unit and whose height is half a unit. The area now is 1 unit for the red square and half a unit for the yellow rectangle, making the total occupied area 1.5 square units. Now in the region that has still not been covered, let me draw a square of side half units with area of 1 by 2 square units. Of course, you must have got the drift by now. We will next add a rectangle whose area is 1 by 2 cube square units then add a red square with area 1 by 2 to the 4 square units, and so on. Now, if you keep on adding more and more of these red squares and yellow rectangles, it's easy to see that as you keep on piling them up, the entire original rectangular area is being covered up. At the same time, it should be pretty obvious that at any given stage, you have not managed to completely occupy the white rectangle. A small corner is sticking out at any given stage. However, the reason why they say that the sum of the areas of all these colored rectangles and squares added together is actually equal to the area of the original white rectangle, that is the sum 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube and so on ad infinitum, is actually 2, is simply that the small amount that is left uncovered at any given stage can be made as small as you want simply by carrying this process out to a higher and higher number of terms. This is basically behind the standard definition that we use of the sum of an infinite series. What we are doing here, of course, is not add up an infinite number of terms. What we are doing rather is starting with one term, S0, which is just the first term T0, in this case just 1, then adding to that T1 to form the partial sum S1, T0 plus T1. In our case, 1.5. Then we add T2 to this result to get the partial sum S2. And we keep on proceeding in this way to obtain a sequence of partial sums S0, S1, S2, S3 and so on. In our particular example, we get the sequence of numbers 1, 3 by 2, 7 by 4, 15 by 8, 31 by 16 and so on. Now it's easy to see that this appears to approach a limiting value of 2. Not only does this appear to approach 2, it's very easy to prove that the limit in this case is exactly 2. After all, adding up the first n plus 1 terms to get Sn will give you the sum 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube and so on up to 1 by 2 to the power n. And this is a very simple sum that we all know how to calculate. There is just a finite geometric series with common ratio of 1 by 2. And the result, as any high school student will tell you, is 1 minus 1 by 2 to the power n plus 1 divided by 1 minus 1 by 2. A simple bit of manipulation, and this can be reduced to 2 minus 1 by 2 to the power n. So it's easy to see that in this case, no matter how big you make your small n, the partial sum Sn will never become equal to 2. However, the gap between this value of 2 and the partial sum, namely 1 over 2 to the power n, can be made as small as you want to just by making n large enough. We will formalize the notion of limit soon, but for the time being, this should make it pretty obvious that for this particular case, at least, the sequence of partial sums is actually converging to the limit 2. And this exactly is the standard definition that we usually use for the sum of an infinite series. To state this formally, given an infinite series, T0 plus T1 plus T2 plus T3, all the way up to infinite number of terms, what we are supposed to do to find its sum is prepare the sequence of partial sums S0, S1, S2, S3 and so on with S capital N, the capital nth partial sum being equal to the sum of small n going from 1 to capital N of T small n. If this sequence of partial sums converge to a limit S, then we say that the infinite series converges and that its sum is S. This, of course, is a standard definition for the sum of an infinite series. If, on the other hand, the limit of the sequence does not exist, we would say that the original series fails to converge and it does not have a sum. Now, if you use this definition for this notorious sum 1 plus 2 plus 3 plus 4 and so on, it is easy to see that the partial sums 1, 3, 6, 10, etc. seem to keep on increasing without limit. An explicit value of the sum of the first n terms, Sn equals 1 plus 2 plus 3 up to n, is a well-known result. It's equal to n into n plus 1 by 2. And this does not approach any finite limit as n becomes larger and larger. Indeed, this result can be made larger than any number you can think about simply by taking a big enough small n. When this happens, we say that the sequence of partial sums fails to converge. In fact, we say that in this particular case, it diverges to infinity. And so, according to the standard definition of the sum of a series, the series 1 plus 2 plus 3 plus 4 simply does not have a sum. Now that seems like quite a dampener. After all, we were trying to understand why this sum is minus 1 by 12 in this series of lectures. And here I am telling you something that you may have already suspected, or in fact known, that this sum does not exist. But note that the sum does not exist according to the standard definition of the sum. Couldn't there be other definitions according to which this sum does exist? But if you were to think about it, isn't the standard definition of a sum the only obvious natural thing to use? The perhaps surprising answer to that question is not really. After all, the standard definition of the sum of an infinite series is just that, a definition. And it's not the only definition possible. Not only that, sometimes even this standard definition can lead to rather weird results, as we are going to soon see. But before we go there, it is obvious that the notion of the limit of a sequence is interconnected rather strongly with the notion of the sum that we are talking about here, and perhaps also with other notions of the sum that we may bring in as alternative definitions. So before we go any further, let me first remind you of exactly what the limit of a sequence really means. Now, given a sequence A0, A1, A2, A3 of real numbers, we say that this sequence converges to a limit L if, for all epsilon greater than 0, there exists a natural number, capital N of epsilon, such that small n greater than capital N of epsilon implies that the magnitude of An minus L is less than epsilon. Now that is a rather lot of Greek and also fancy symbols. But if you strip it of all this, the definition isn't really very difficult to understand. All that it says, if you throw away a sufficiently large number of terms from the head of the series, you can pack the infinitely long tail of the series that is left as close to the number L as you want. Now what does this as close to the number L really mean? It really means no matter how finicky you are, no matter how small a value of epsilon you prescribe, you can always ensure that by throwing away enough number of terms from the head of the series, the rest of it can always be put inside this small interval between L minus epsilon and L plus epsilon. Let us take a look at the example of the sequence of partial sums of the series 1 plus half plus 1 by 2 square plus 1 by 2 cube plus all the way up to infinity. We have already seen that its sum is 2. That is, the sequence of partial sums actually converge to the number 2. But let us see exactly what that means by plotting these points 1, 3 by 2, 7 by 4, 15 by 8 and so on a number line. As you can see, the green points which indicate the partial sums are rather spread out at first, but they soon crowd around each other and ultimately seem to go to a limit, this red dot L that you can see right now. And if you were to cut off a region from L minus epsilon to L plus epsilon, that is an interval of width twice epsilon centered at L, a few of the initial points will lie outside this particular interval, but the rest, the infinite tail of this sequence, will all fit inside that interval. If you make epsilon smaller, the interval that you're cutting out from the real line becomes smaller, and that might mean that a few more terms from the head are now outside this interval. But once again, if you throw those points away, the rest of the infinite tail is entirely inside the interval. This is exactly what we mean by the epsilon delta definition of the limit. Now, though this is precisely the definition of the limit that one uses in mathematics, there is a small problem with this. In order to actually use this definition, you need to know exactly what the value of L is. After all, the definition tells you that you should be able to pack the tail of the sequence entirely inside an interval from L minus epsilon to L plus epsilon, no matter how small epsilon is. However, if you do not know what the L is, then you wouldn't know which interval you're really talking about. If you were to guess at an L and you found that the tail of the sequence does not actually fit entirely inside this twice epsilon width interval around L, that definitely means that L is not the limit of the sequence. However, this could either mean that there is no such limit at all, or it could simply mean that there is a limit, you're just barking up the wrong one. It would of course be great if we could figure out whether a sequence converges or not just by looking at the numbers that are there in the sequence itself, without bothering about external entities like the limit L. It turns out that there is a way to figure this out. First, let us take a look at what happens when a particular sequence does have a limit. In the definition of the limit, the number epsilon was an arbitrary positive number. So we could in particular choose epsilon by 2 to be the half-width of the region centered around L. The definition of a limit tells us that for any such epsilon, there will be a capital N epsilon such that all numbers an where small n is bigger than capital N epsilon will be within a distance epsilon by 2 of the limit L. That is, they will all be within this particular interval that you can see shaded off right now. But that means that the maximum possible distance between any two of them can never exceed epsilon. In other words, if the limit L of a sequence exists, then we must have the following. For every positive epsilon greater than 0, there has to exist a capital N epsilon such that if m and n are natural numbers both exceeding capital N of epsilon, then mod of am minus an, the distance between am and an, has to be less than epsilon. As we have just proven, every convergent sequence must have this property, and a sequence which has this property is called a Cauchy convergent sequence or simply a Cauchy sequence. As we have shown, every convergent sequence has to be a Cauchy sequence. On the other hand, if you are dealing with a sequence of real numbers, then the converse of this statement is also true. A sequence is convergent if and only if it is a Cauchy convergent sequence. Now this happens to be a very deep property of real numbers. In a sense, you can even say that this is the defining property of real numbers. We will not go into details of all that because this is all standard stuff that you can find in calculus textbooks. Let us now go back to this issue of showing that the standard definition of the sum of an infinite series is not completely natural or obvious, that even that can lead to some rather weird results. In order to do that, we will make use of another series which uses whole numbers, a bit indirectly. Not really a series made out of whole numbers, but a series whose terms are reciprocals of the whole numbers. And not only that, they come with alternate signs. So the series that we are looking at here, S, is given by 1 minus half plus 1/3 minus 1/4 plus 1/5 minus 1/6 and so on. It so happens that this particular series is convergent. Let me first prove this. Of course, in order to show that this series converges, we have to show that the sequence formed by the partial sums converge. Let us take a look at the difference between Sm and Sn, the nth and the mth partial sums. Here m and n are both positive integers, and for the sake of definiteness, let us take n to be bigger than m. Then mod of Sn minus Sm simply involves all the terms in the series up to 1 by n, from which you take away all the terms up to 1 by m. So this is given by 1 over m plus 1 minus 1 over m plus 2 plus 1 over m plus 3 minus and so on, and it ends with a 1 by n, which may have either a plus sign or a minus sign. Now before we go any further, let me first convince you that this really is the magnitude of Sn minus Sm. After all, the term 1 by m plus 1 in the original series may have come with either a plus sign or a minus sign, so it would be perfectly legitimate to ask whether this one that we have written down is the magnitude of Sn minus Sm, or whether minus 1 by m plus 1 plus 1 by m plus 2 minus 1 by m plus 3 and so on up to the 1 by n term is actually the magnitude. In order to show that this is the one that is really the magnitude, I have to show that this is positive. That actually is pretty easy to do. All you have to do is pair off the terms as they stand. 1 by m plus 1 minus 1 by m plus 2. To that you add 1 by m plus 3 minus 1 by m plus 4 and so on. Here you have a sum of a lot of terms, but it's easy to see that each and every one of these brackets is positive, because in each one of them you are taking away the reciprocal of a larger number from that of a smaller number. The only thing that is left out of this is the final term plus or minus 1 by n. And there it's very easy to convince yourselves that if the sign in front of that is a plus, then after you have paired off all the terms, this plus 1 by n will be an odd man out. But it will of course add to all the results that you have had so far. If the sign in front of 1 by n happens to be negative, it will actually be a second term of one of these pairs. In either case, it's easy to see that you're adding a lot of positive numbers together, so the sum has to be positive. And so, this really is the magnitude of Sn minus Sm. Now that we have established that, let us next show that this actually is bounded above. In fact, you can show that very easily by again pairing of the terms, but this time leaving 1 by m plus 1 out. So what you get is 1 by m plus 1 minus, within a bracket, 1 by m plus 2 minus 1 by m plus 3, then minus 1 by m plus 4 minus 1 by m plus 5, and so on. In this case, what you will see is you are actually taking away a bunch of terms from 1 over m plus 1, each of which is positive. You should also be able to convince yourself that in this case, the 1 by n, no matter whether it comes with a plus sign or a minus sign, actually ends up subtracting from 1 by m plus 1. So, the magnitude of Sn minus Sm happens to be less than 1 by m plus 1. But this result tells you that you can make the gap between partial sums Sn and Sm as small as you want to simply by making m and hence n large enough. Thus, our sequence of partial sums is a Cauchy sequence, hence it converges, and so our series converges. Well, not only is this series convergent, we actually know what the sum is. The sum happens to be the natural logarithm of 2. There are many ways of proving this result. Let me just give you one very simple way. It's easy to see that log of 2 is the result of the integration of 1 over 1 plus x with respect to x from x equal to 0 to x equal to 1. But now, if you write the 1 over 1 plus x, which is 1 plus x to the power minus 1, in an infinite series using the binomial theorem, you get to see that this is the integral from 0 to 1 of the infinite series 1 minus x plus x square minus x cube and so on, all the way up to infinity. And it's trivial to carry out the integration term by term and land up with 1 minus half plus 1/3 minus 1/4 and so on. Now, for what is to follow, the precise value of the series is really of no consequence, but it is gratifying to know that it has a well understood value for its sum. By the way, those of you who know the series of log of 1 plus x as x minus x square by 2 plus x cube by 3 and so on, could also figure out an alternative way of seeing that the sum of the series is actually log 2 simply by putting in x equal to 1 in this expansion for log of 1 plus x. Let us now do something rather simple with this series. Note that this series is one of reciprocals of whole numbers. The reciprocals of even whole numbers come with a minus sign, and those of odd whole numbers come with a plus sign. What I am going to do next is simply rearrange the terms of the series. We will do this in a way that ensures that each and every one of the terms are accounted for and they come with the same sign as in the original series. So it should be rather obvious that we are writing the same series once again. The way I do this is the following. I first write down all the reciprocals of the odd whole numbers. 1 by 1, 1 by 3, 1 by 5 and so on, of course with plus sign. As you can see, I have left gaps between these numbers, and it's rather obvious that I'm going to put in the rest of the numbers, the ones with the even denominators, in those gaps, but we will not put them all in at once. What we will do is first we are going to write down exactly half of the numbers that we have written down next to them, of course with a minus sign. That is, 1 by 1 will be followed by minus 1 by 2, 1 by 3 by minus 1 by 6, 1 by 5 by minus 1 by 10 and so on. Now it's obvious that at this stage we have not written down all the terms of my original series. All the terms with odd denominators are in place, but among the terms with even denominators, we have just written down those whose denominators are double odd integers. And that means that the multiples of 4 have not been accounted for. So in the gap that is still left, I'm going to put in the reciprocals of multiples of 4, obviously with a minus sign, 1 by 1. So you have 1 by 1 minus 1 by 2 minus 1 by 4. Then you have 1 by 3 minus 1 by 6 minus 1 by 8 and so on. Now if you look at the pair of terms at the beginning of each of these triplets, it's easy to see that there you're taking away half of a number from itself. The result, of course, is the half of the original number. Carrying out that calculation leaves us with the series half minus 1/4 plus 1/6 minus 1/8 plus 1/10 and so on. A series of reciprocals of even natural numbers only. Now it's obvious that I can take 1/2 common out of this, but that will lead to a very surprising result. The series S is equal to half of 1 minus half plus 1/3 minus 1/4 and so on, which means S is actually equal to half of S. And since S is neither 0 nor infinite, we can definitely cancel this out and we end up with a wonderful result. 2 equals 1. Obviously, this result is wonderful because it's patently false. So somewhere down the line, we must have made a mistake in the logic. Now, many of you may have already seen many 2 equal to 1 proofs earlier, but almost inevitably, those proofs use something illegitimate like dividing by a 0 or by infinity or something of that sort. We have done no such thing here. I would urge you to think about exactly what went wrong here. If nothing else, this will help you to realize why the standard definition of the sum of an infinite series is not necessarily gospel truth, and why looking for alternative definitions may not be such a bad idea. We will come back to this in the next lecture. Bye for today.